In this video, we look at the evaluation theorem. Now, the evaluation theorem is already 50% of the fundamental theorem of calculus. Okay, so remember we have used the integral sign in two different meanings. Right here on the left, we use it for the indefinite integral, which in fact is another way to write down an antiderivative. Here on the right, though, we write it as integral from a to b, so we put boundaries on the integration. And now it has a very different meaning, right? Now it is the signed area between the x-axis and the curve. And remember, this integral can actually be positive or negative, depending if the areas are above or below the curve. And the definite integral was defined by the Riemann sum. And now the question arises, how is one related to the other? And the answer is given by the evaluation theorem. It will make a relation between the antiderivative on the one side and the signed area on the other. Okay, let's go right to it. Assume f is a continuous function on the interval a to b, then the definite integral from a to b f of x dx can be actually evaluated by using the antiderivatives. So this integral is equal to capital F of b minus capital F of a, where capital F is an antiderivative of little f. So either you write f prime is equal to little f, or you write big F is the integral of little f. These are equivalent notations for an antiderivative. And so knowing the antiderivative allows you, in fact, to compute a definite integral. So this is a big thing. This is a big deal. Let's look at a simple example to start with. Earlier we have looked at an integral from 0 to 1 of x squared dx. That was the area under the parabola between the point 0 and the point 1. As we did this with the Riemann sum, we found values which got very close to 1/3. So we could kind of guess that the limit is, in fact, 1/3. But now let's use the evaluation theorem to check this out. So what do we have to do? We have to identify, first of all, the function f. So the function f is x squared. Secondly, we have to identify the antiderivative, so which is 1/3 x to the 3 plus a constant. And so then we can apply the above formula. So according to the formula, we have the integral from 0 to 1, x squared dx, would be then f, big F, at 1 minus big F at 0. So let's sub this antiderivative in. So we get 1/3 times 1 cubed, which is just 1, plus this constant, minus 1/3 0 cubed, which is just 0, and then minus c. So right, the minus sign carries through. So this is 1/3. Wow, isn't that cool? So first of all, we confirmed that we get 1/3, but secondly, we actually found a very simple way to compute it by just using the antiderivative. Before I continue with the examples, though, I would like to introduce a new notation for the evaluation theorem. So here we have f of b minus f of a, and this is often written in this form. You use the antiderivative f of x, and then you do a long line or a line with some hooks on it, and you evaluate it from a to b. So this expression means capital F evaluated at b minus capital F evaluated at a. Another notation which you also find often is f of x just using a line between a and b without the hooks on the line. Okay, so those both notations will show up, and they mean this is the difference of the function capital F between b and a. So here are two examples. The first one, integral from 0 to 4, 6x minus 1 over square root of x dx. To evaluate this, we use the evaluation theorem, which means we first identify little f of x, which is 6x minus 1 over root x, and then we need an antiderivative, which is capital F of x is 3x squared minus 2 root x. Right, if I differentiate root x, I get 1 over 2, 1 over root x. So that's correct, plus a constant. And then I continue my integration, so by the evaluation theorem, this is f of x between 0 and 4. So that's one way to write it. or we can write it as f of 4 minus f at 0. And so now I take this function which I just found, I take the antiderivative, sub it in there, and get the numbers. So let's do this. F of 4 is 3 times 16, which is 48, minus 2 times root of 4, which together is 4, plus a constant, and then we evaluate the whole thing at 0. So then the first term is 0, the second term is 0, and the last term is minus c. The constants cancel each other, and we get 44. And we are done. Let's look at the second example. Integral from 0 to 1, x to the e plus e to the x. Wow, that's a funny example. Okay, let's do the same story. So f of x is x to the e plus e to the x. Capital F will be an antiderivative. So this is 1 over e plus 1 x to the e plus 1 plus e to the x plus a constant. Then the integral is f of x, so the antiderivative between 0 and 1, or we write this as f of 1 minus f at 0. So we sub in 1 into the antiderivative and use that here. So if we sub in 1 in this term, we get 1 divided by e plus 1. Then e to the 1 is e, and then c is a constant, minus, and we sub in 0. The first term is 0, next term is minus 1, and then minus the constant. So the constants cancel, and we get 1 over e plus 1 plus e minus 1. Now, if you like, you can bring this on a common denominator. I skip a few steps here, and we get e squared divided by e plus 1. So isn't that fast? I mean, imagine, look back at this integral here, x to the e plus e to the x. Looks a bit complicated. And if you have to do it with the Riemann sum, you go maybe nuts. So the evaluation theorem helps us quite a bit. Now, before I summarize, I like to discuss a few properties of definite integrals. And these properties are very similar to those of indefinite integrals, of course. So for example, number 1, integral ab over a constant c dx. So that would be c times b minus a. Right? If you use the fundamental theorem, you can easily do this. So if f of x is c, then capital F of x is cx plus a constant. Okay? And then if I do my f of b minus f of a, I get c at b plus capital C minus c at a plus capital C, which is c times b minus a as written here. Now, if you have two functions which you add or subtract, so for example f plus g integral, then this is the same as the integral of f plus the integral of g. Or if you have a subtraction, then the subtraction carries over. Here third, if you have a constant multiplying f and then you integrate, that is the same as taking the constant out of the integration. And then finally, if you have an interval from a to b, which you divide into a subinterval a to d and d to b, then the integral from a to b of x dx is the same as the integral from a to d plus the integral from d to b. You can split up the integral over a whole domain into subdomains and add them up. Let me summarize. So if f is a continuous function on an interval a to b, then the integral from a to b f of x dx can actually be written using the antiderivatives as f of b minus f of a. And a great notation for this is this vertical line, or the vertical line with the little hooks on it. So it is f of x between a and b. Capital F can be any antiderivative because we have seen in the examples the constant cancels. So whichever antiderivative you have handy, use it and it will work. Oh, hey! Hey, see who is visiting me in my studio. Hey, Tolo, how are you doing? Hi, everybody. Tolo, why don't you say to our listeners what you think about the evaluation theorem?